It's time to look at forces as they pertain to circular motion. We want to recall back from previous lectures that we talked about a centripetal acceleration, and we said that the centripetal acceleration was equal to the speed squared divided by the radius of curvature. Now in the case of uniform circular motion, the speed never changes and the radius of curvature never changes. But we're going to stretch away from that a little bit and look at situations where the speed and or the radius might change. Oftentimes we'll refer to this as normal acceleration because it's always going to be normal to the curve. Even if you consider uniform circular motion, you'll recall that the centripetal acceleration was towards the center of the circle, and that would be normal to the tangent to the circle. And so this term normal acceleration is applicable. And this will include even situations where the curvature might be changing. If I'm at this location here on this path, there is a tangent to that curve, and the normal acceleration will be at 90 degrees or normal to that tangent. And so the normal acceleration will be the speed squared divided by the radius of curvature. Given this situation then, there has to be a centripetal force. Something has to be allowing that object to make the turn. And so the question will be is where on our force diagram do we show the centripetal force, and where in the force equations will we show the centripetal force? And this will be a critical issue for this lecture. Okay, so again recall the centripetal acceleration is equal to the speed squared over r, the radius of curvature, and the speed, if this is a circular motion, the speed will equal the circumference divided by the period. This is only applicable if I have uniform circular motion, but for the majority of this class that's what we'll be working with. So the circumference of a circle is 2 pi times the radius, and the period of motion we just labeled as t, and that again is the time it takes the object to make one complete revolution about that circle. So if I was talking about the second hand on a clock, its period of motion is 60 seconds. Well, if I take that v and I square it, then v squared is equal to 4 pi squared r squared divided by the period squared. And if I substitute that up into this equation, then I get the normal or the centripetal acceleration, same thing, to equal 4 pi squared r divided by the period squared. Alright, so let's run through an example. Let's say I have a mass on a turntable, and the turntable will be undergoing uniform circular motion. So the mass is also, and the idea is I want to figure out what's it going to take to keep the mass on the turntable undergoing uniform circular motion. So from a top view, the turntable might look like this, and then the mass would be at some location on that turntable. And we'll have the turntable rotating in a counterclockwise direction. Now the mass, if there's no friction or something to keep it into place, is going to slide off of the turntable. Or if there's no friction whatsoever, that's just going to stay in its position while the turntable undergoes rotation. But let's assume that it's got some sort of frictional force and it's going to stay on that table. So if I do a side view, then the turntable might look something like this. And here's the mass on top of the turntable. And the center of curvature is going to be right there in the middle of the turntable. So let's draw a force diagram then on that mass. So we know that there is a gravitational force, and that's going to be pointing down. And again, as in the past, that's gravity. That is, of course, due to the Earth. And that's acting on the mass. In addition, there's a normal force pushing up. And that normal force is going to be due to the turntable. Right, that's the surface that it's standing on, is the turntable, and that's also a force acting on the mass. And finally, there's going to be a force to the left, and that's going to be a frictional force in this scenario. I'm just going to say it's a force due to friction. All right, so that's a frictional force that's due to the turntable, and that's acting on the mass. So there are my forces. Now you'll notice there's no centripetal force in here. The centripetal force in this scenario is due to the friction. That is to say, the friction creates the centripetal force. The centripetal force in and of itself will not be part of the force diagram unless I draw in the acceleration, and then it's the centripetal acceleration. But the critical issue here is something has to cause the centripetal force. In this case, it's a frictional force due to the turntable. If I were swinging a ball on a string, it would be a tension due to the string that would be creating the centripetal force. There is a net acceleration in this case, and it's towards the inside, and that is the centripetal acceleration. The net acceleration, the right-hand side of my second law equations, is where the centripetal acceleration will come into play. So if I look at the sum of the forces in the y direction for starters, I have the normal force minus mg. That's equal to the mass times the acceleration in the y direction. But there is no acceleration in the y direction, so that's equal to 0. The sum of the forces in the x direction, I only have one, and that's the frictional force. And it's pointing to the left, so we better put in an axis. So we'll make x to the right, and y is up as the standard set of axes. And so minus F equals minus ma, and that acceleration is, of course, centripetal. Now, if the mass is not moving, and we'll assume it's not going to move, then the frictional force is a static frictional force. Now recall, static friction is less than or equal to some coefficient times a normal force. And so in this scenario, I don't know if I've reached that maximum point yet. Now, if the problem says something like, how fast can the turntable spin before the mass slides off, in that scenario, because I've used this extreme case, before the mass slides off, how large can the frictional force be? Then I know that that has become an equal sign. But until that point, the frictional force will be as strong as it needs to be to keep the mass in place on the turntable. And so you've got some sort of a system here that you'll have to take care of, and it depends on what's been given in the problem. Now, a conical pendulum is basically the mass on the end of a string, and it's rotating in a horizontal circle. So at different positions, it might be here or it might be over here. Just depends on the scenario, but it moves around in a circle, and that's generally a horizontal circle, so parallel to the floor. And as it goes around, it takes a certain amount of time to reach from one side back to that same side again. So let's analyze actually the mass as it's over here on the left-hand side. So here's the mass, and as I examine forces, there is a gravitational force. So there's gravity, and as always, that has been due to the Earth, and that's acting on the mass. But there's also a tension, and that's up and to the right. So there's a tension here, and that's going to be due to a string that's been attached to the mass. So that's acting on the mass. And that's it. There's nothing else touching the mass except for the string, and then of course the only long-range force we have is gravity. So we'll still set up a standard x and y axis. And this object is moving around with a constant speed. So in the direction tangent to the circle, there is no acceleration. So let's get rid of that. But there is an acceleration towards the center. All right, so there's an acceleration here, and that is a centripetal acceleration. And it's always pointing towards the center. So again, we could call that a normal acceleration, but we'll stick to centripetal for now. Well, given that scenario, I can do a sum of the forces in the x and a sum of the forces in the y. I'm going to have to define some angle theta, and I'm going to use this angle in here. And the reason that I do that is that by alternate interior angles, that's going to be the same as that angle theta, the angle that the string makes with the vertical. The angle the string makes with the vertical. And so in the x direction, there's a component of the tension here that's opposite the angle theta. So that must be t sine theta. And that's the only force in the x direction. So that must equal mass times the centripetal acceleration. So the tension, or in this case a component of the tension, is what is yielding the centripetal force. So the horizontal component of the tension gives us that centripetal force. And then in the y direction, I have t cosine theta. That's this component of the tension along the vertical direction, and it's upward, minus mg, but there is no acceleration in the y direction, so that's equal to 0. And so I know something about my tension. If I know the angle theta, I can solve for the tension in terms of the mass and gravity, and then I could substitute that back into the x equation once I have it here and figure out what my centripetal acceleration is. Another classic problem is a loop-the-loop. So imagine you have some sort of a car, or a cart perhaps, moving down a track, and it comes across the loop-the-loop, and I'm interested in the centripetal motion at a couple of different points on that loop-the-loop. Now in this scenario, the speed might not be constant. So let's do a force diagram in both of these positions, position 1 and position 2. We'll start off in position 1. There's a gravitational force, as there always is. So that's gravity, that's due to the Earth, and that's acting on the cart. Now the only thing in contact with the cart is the track, and so in this direction there'll be a normal force, because that's normal to the track. So there's a normal force, and that's due to the track, and that's acting on the cart. And that's really all there is. Now in this scenario, I'm going to change my axes a little bit. So I'm going to have one axis parallel to the track, or tangent to the track. So I'm going to call that E sub t for tangential. I'll put a little caret over the top. That's a unit vector. And then there's another one that points inward, and that's in the normal direction. So I'm going to call that E sub n for E normal. Again, the little hat indicates that's a unit vector. So there's some angle theta here. And if I look at the track, then this is also the angle theta. And so when I do the sum of the forces, I'm going to have the sum of the forces in the normal direction. And in that case, I'm going to have F normal minus mg cosine theta, because this is the component of gravity along the normal unit vector, but it's in the opposite direction of E normal, so that's the minus sign. Now the acceleration has to be inward, so there's my normal acceleration. There will also be a tangential acceleration. We're really not going to worry about that at this point in the game. We're just interested in the normal acceleration, but that's v squared over r. So this equals mv squared over the radius of this loop-the-loop. So I'm going to need to know what the v is, what the velocity is at that point. And we'll use some techniques later on in this course using energy to figure out what that speed is compared to the speed we had over here. So I'm going to put a v0 there, and I'm actually going to put a v1 over here. And so that's the normal force equation when the cart is in position number 1. Now position number 2 is a little more interesting, so let's take a look at that. So here's the cart in position number 2. So as I look at the forces, there is a gravitational force still. So that's gravity due to the Earth acting on the cart. And there's also a normal force, and that can have a lot of different values, as we'll see here in a little bit. So that's a normal force due to the track acting on the cart. I'm going to continue my axes in the same direction, so my normal is pointing down now, because that's the direction that is normal to the track. And here's tangential. We're not really concerned with tangential in this part of the problem, especially because there are no forces acting in the tangential direction. Since there's no forces tangential, there's only a centripetal acceleration, or a normal acceleration. And so the sum of the forces in the normal direction, I have F normal plus mg. Now notice they're both positive, and that's because E normal is pointing down, and that's the positive normal direction, and that's going to equal mv squared over r. So depending upon my speed, my normal force can have a lot of different values, but the gravitational force is constant. It doesn't care how fast I'm going. But you can imagine if you're going very fast, the track is going to push down to keep you into that turn. But if you're not going fast enough, what's going to happen is you're not going to make it around that turn. The normal force is going to drop to 0, not going to hold on to the cart, and you might fall. Now, there is a limiting case, and again we'll talk about this when we discuss energy later on. There is a limiting case when the normal force just goes to 0. The cart will make it around the loop-the-loop, but just barely. Now the banked curve is another idea, and this is going to occur when you create a highway, for example. So here's the highway, and in general, as a car goes around that turn, it's got to stay in the turn. Now friction will oftentimes keep you in the turn, but a lot of times the highway will also have an embankment to it. So it might look something like this. If you were to cut a portion of the highway across this cross section, you would see this embankment. And so the car going around that turn would be on a slight banked curve like that. So the center of curvature is to the left in this drawing. So as I identify forces acting on the car, there's my car, and that could be a rear view, for example. I'm going to have a gravitational force, just like I always have here. That, of course, is due to the Earth acting on the car. And there's also a normal force. Now that's normal to the surface, so that's got to be perpendicular to that surface. So there's F normal, that's a normal force. And that's going to be due to the road acting on the car. And then if the car goes too fast, we know it's going to slide up in this direction. And so if it's going too fast, there must be a frictional force downward, because it wants to slide up. Remember, friction is going to oppose that desired motion. So this would be a frictional force. That is due to the road, and that's acting on car. Now the axes in this scenario are a little different than you might have thought. In past problems, we put the x-axis along the incline and the y-axis perpendicular to the incline. We're actually not going to do that this time. Turns out that makes the math more complicated. We're going to have a normal axis towards the center of curvature, and then I'm going to have an upward axis, which I'm just going to call the z-axis. Now, if the car is not speeding up or slowing down, the only acceleration is towards the center of curvature. So the normal acceleration is along the normal axis. Now, if the embankment has some angle theta, then we know from previous discussion that this is also the angle theta here. There's my normal axis and my z-axis. I have a gravitational force down, normal force, I have a frictional force. Now, the frictional force and the normal force are at 90 degrees to each other. And if I extend that out a little bit, the frictional force is along the axis, so that's the angle theta, and that's the angle theta. By vertical angles, this must also be theta, and this must also be theta. Again, that's based on the vertical angles. This is the vertical angle to that. This is the vertical angle to that. Remember, vertical angles are when two lines cross. This angle and this angle are vertical angles, and they are congruent. You got to dig back to your geometry on those. Recall the normal acceleration was in that direction. So as I look at the sum of the forces, I'm going to have the sum of the forces in the z and the sum of the forces in the normal direction. In the z direction, I have minus mg. That's the easy one. Remember, this is the z direction here. Then there's a component of the normal force in this direction, the z direction, and that's going to be F normal cosine theta. And there's a component of friction in the normal direction. That's right there, and that's down, so minus F, so F sine theta. That's going to equal 0. This is a plus sign there because the normal component is pointing up. Then in the normal direction, gravity has no component in the normal direction. But here's a component of friction in the normal direction. That's F cosine theta. And that's in the normal direction, so that's positive. And then here's a component of the normal force in the normal direction. And that's going to be plus F normal sine theta. Got to be a little careful on these terms, normal. This is normal to the curve, and this is normal to the curvature of the motion. They're not the same normal. And this is going to equal then mv squared over the radius of curvature of the road. So you'll see in this problem, finding that normal force is really a little bit more complicated because it's here. It's also going to be in the frictional equation, or it might be. Because again, if this is static friction, the car is not sliding along the road. This is less than or equal to mu static times the normal force. If it is sliding, then it's kinetic friction. That's not a good thing, but at least we would know that it's mu kinetic times the normal force. So in an interesting scenario, we're looking for the actual maximum or minimum speed that I can have before I do slide. And in that scenario, my static frictional force inequality becomes an equation because I've reached that maximum possible value. The algebra here we're not going to play with at this point in time, which is not to say you won't play with it in the future.